the last few classes, we discussed in detail the different types of dislocations which can form in FCC lattice, okay, and the various ways in which different type of dislocations can split into partials. All these things we have looked at it. Other important crystal structures in which most of the metals, especially important metals like iron, titanium, zirconium and all these materials, are transition metals like molybdenum, niobium, chromium, all these crystallize into is BCC or HCP structure. What we will do today is to look briefly at dislocations in BCC and HCP type of metals. When we look at the crystal structure of BCC, what are the vectors? Okay, we can consider the small translation vectors, perfect translation vectors. They are, if you look in increasing order of magnitude, half 111 type, 100 type, then comes 110 type. Okay, if you look at these translation vectors, okay, the one which will qualify or which can qualify to be the Bijus vector for the dislocation in BCC lattice is half 111. Okay. If you look at the crystal structure, that is the shortest, not only the translation vector, that is the close pack direction also. Because in fact in BCCs there is only one close pack direction, which is along 111 direction. Okay. This 111 direction, okay, can lie along essentially 6 110 planes. Okay, that is if we consider the number of slip systems, that is in each 110 plane, if we consider, there are 2 close pack directions are there. So 6 planes are there. Totally we will have 12 slip systems. Similarly, if we consider 112 plane, that's because in BCC structure 110, 112 as well as 123, all of them have got almost the same packing density. So the dislocations can move on all these planes, whereas in the case of FCC which we considered, there 111 is the close packed structure. Here none of the structures are close packed, but they have got almost the similar packing density. They are the best which packing density which is available in terms of the various types of planes which we can consider in BCC lattice. Because of that, okay, 112 plane also could be a potential slip plane. There only one 111 direction is there, but there are 12 111 planes are there, so 12 slip systems are possible. Then if you look at 1 to 3 a plane also, there is only one 111 direction is there, okay. But 1 to 3 planes if you consider, there are 24 planes are there, distinct planes. So if we look at the total number of slip planes which are available for a particular dislocation, perfect dislocation in BCC, there are total 48. Let us look at the case of any particular 111 direction. That direction, any particular specific 111 direction if we take it, that can be contained by 3 110 type of plane, okay. Then 3 112 type of planes and 6 123 type of slip planes, okay. All of them, okay, the common intersection could be a specific 111 direction. So if the dislocation is a screw dislocation, the dislocation can easily cross slip from one plane to the other without any problem. Okay. So cross slip becomes very easy. So it will be merely moving from one plane to the another depending upon the way in which the maximum critical resolved shear stress is there. Because of this, the slip gives a wavy appearance. Okay. Whereas in the case of FCC, it's specified that this is the plane in which the dislocation moves. Here there are so many possibilities are there. And since all of them have got one or the other, because since all of them are inclined with respect to each other, one plane or the other will have the maximum resolved shear stress so that it can easily move. If we take pure iron at room temperature, okay, since we consider that for each direction there are essentially about 12 planes are possible around that. This direction around 12 planes will be there. So some plane or the other will have a maximum critical resolved shear stress, as I mentioned, so that slip can easily propagate. Okay. But there are many systems, or even in iron itself, if we do alloying because of some expansions, okay, and it has been seen that sometimes the slip systems are restricted. For example, if we take iron silicon alloys, okay, essentially the slip occurs in this, or the slip is restricted to 110 type of planes. Okay. Whereas if you look at edge dislocation, the line direction, the Burgess vector is not the same. Okay, not in the same direction, Burgess vector and the line direction. Because of that, we can define a slip plane, okay, and this plane is unique for each slip system, so cross slip will not take place. If you look at the various directions, each of the direction, okay, we can look at how atomic layers are packed. If you look along 001 direction, okay, it is an AB type of a stacking, whereas if you look along 112 type of a direction, okay, it's a 6-layer stacking sequence ABC, no, not ABC, ABCDEF, ABCDEF, like that it goes. Along 111 plane, the packing is ABC. Along 110 plane, which is the close packed plane, the packing is a AB type of a packing. Okay. Let us just look at the structure of dislocation, okay, in 110 plane. If you look at it, this is a packing along 001 plane. Okay. If it is an A layer, the B layer will be coming on top of it. So this is at the position from which, okay, it's at the low symmetry position. It is quite stable. It just doesn't move because we are looking at the hard sphere model. If we look at 110 plane, here also the packing is an here also the stacking is essentially a AB type of a stacking. But if you look at the atom which is sitting on here, it's sitting at a position where either it will move to this direction or to this direction because of the low energy positions. But from symmetry consideration, atom has to sit at this position. Okay. So on this basis, people thought that fault could form. Okay. Here essentially what we are trying to do is we are just looking at how atom which is sitting on the top of it, it should be moved to an identical position by a moment of A by 2 112, A by 2 111, okay, dislocation. Okay. So atom sitting on the top, it just comes to a position which is a slightly low energy position. From there it shifts to another low energy position, from there it shifts to a higher energy position. That is how it can reach. So this itself, okay, can be represented by just vector of the perfect dislocation splits into 3 dislocations, one with 1 by 8, 1 bar 0, another with 1 by 4, 1 bar 2, okay, then plus 1 by 8, 1 bar 0. That is this sort of reaction has been proposed by Cohen and Crusard, okay. But when people looked at it, that means that if you look at the Burgess vector of these dislocations are not the translation vectors in BCC lattice. Because of it, the movement of these dislocations should create a stacking fault, correct? But experimental evidence did not show any stacking fault in most of the BCC material, okay. They were seldom seen, okay. So then they thought that the fault energy may be very high, okay. Because of this, only cross slip takes place. They don't split into partials, because if the dislocation split into partial, as we have seen in the case of FCC material, if they have to cross slip, they have to join together. The partial should join together, form a perfect dislocation, then only they can cross slip, okay. And in most of the BCC material, cross slip has also been found DC. This is what essentially was the sort of a argument which has been put forward, or a reasoning which has been put forward. Later, in recent times, people have done a lot of computer simulation work, and detailed computer calculations have been done taking elastic anisotropy, all these factors into consideration. And they had also observed that faulting is highly unlikely in BCC material, okay. So far we considered about faulting. Now let us look at the core structure of the dislocation itself, okay. Lot of simulation work has been done to look at how the core of a perfect dislocation looks like in BCC, okay. This is from the work of Vitek, okay. Essentially the dislocation line, okay, or the Burgess vector comes out of the screen perpendicular to a screen. Whatever the atom positions which are being shown on the screen are 110 type plane, okay. Burgess vector is perpendicular to it, okay. And we know that around the dislocation line direction, okay. Now we are looking for how the displacements of the atom are taking place. They are being shown by arrows, okay. So after these computer calculations, they had just marked the position of atoms on 110 plane, and when the dislocation core is there at this center, okay, how the displacements are taking place. Is it has a radial symmetry or not? When we look at the figure, it's obvious that it doesn't have a radial symmetry, and in these directions the displacements are very high, okay, and in this as well as in this direction, and this corresponds to the plane on which these directions are lying, are 110 type of a plane. So essentially the displacement around a screw dislocation, okay, that is around the core of the dislocation, has split on 3 110 type of planes, which contains the dislocation, okay. This figure, what we are showing, it is a stereogram, okay, and the stereogram shows the various directions. This is 111 112 type of a direction, and this is the plane. In this plane it will contain. So if we look at it, these directions we can identify using this stereogram, okay. So this is the type, that is half 111 dislocation can split into 3 1/6 111 type of a Burgess vector it can have, okay. Each of them will be along 3 different 110 type of a plane they can lie. That means that since the core is lying on different planes, if the dislocation has to move, it is not very easy, because they are on 3 directions. It has a Burgess vector, component of the Burgess vector in 3 planes, correct? Similarly, if we look very carefully, we can notice that even in these directions also, we can see some asymmetry of the displacements could be seen even on 112 planes also. There is some part of the component of the split into there is especially 1/6 111, part of it is in 110 type of a plane, part of it is in 112 type of plane. But what is essentially interesting is that if we try to deform this material, okay, then what happens is that at different stresses, okay, here is a very small stress that's essentially it's something like 1/100th of a close to the shear modulus. It's a quite high stress. When that stress is being applied, the displacements, now you can see that an asymmetry has come. Only in this direction the displacement is maximum and the displacement in these directions have reduced. The same thing you can see it when the magnitude of the shear stress has been increased. You can see that now it is lying in only one particular 110 type of a plane, correct? The component of the vectors in that component of the bias vector which is there in other two 110 type of planes, that has become 0. Okay. Now it will start moving. Okay. So this is what one peculiarity of dislocation movement, especially screw dislocation in BCC lattice. Okay. And it's a little more complicated than what it appears, like in the case of an FCC material, okay, because of which there is a difficulty for screw to move, and most of the material it has been observed that very long screw dislocations had been noticed in BCC type of materials, okay, and whereas hardly any H type of dislocations are seen. Okay. Let us look at the case of a non-screw dislocations, how the core of a dislocation. What is the observation which has been obtained? That either the core lies on 110 plane, that entire displacement, most of the displacement lies on that plane, so that it is easy for them to move, okay, but at the same time no stacking fault has been observed, okay. And another observation which is there is that in the case of FCC material, okay, when we apply a shear stress for an edge dislocation, it's very sensitive to the application of the not only the shear stress, non-shear stress components, okay, like a tensile stress which we apply, okay, lot of vacancies will be because it will climb up or down, lot of vacancies are generated, okay. That sort of a sensitiveness to a non-shear stress has not been observed for dislocations, perfect dislocations in BCC material, okay. And another observation is also that compared to screw dislocations, since the core is essentially confined to a slip plane, it's easy for them to move, and that move at very small shear stresses. Okay, so far we have considered the shortest translation vectors. Okay, the observation in BCC is that 001 type of a dislocation has also been observed. Okay, when we deform BCC material, we have noticed that every slip plane, especially 110 type of a plane, contains two close packed directions. Okay, two dislocations are possible. During deformation, some of these dislocations can interact. For example, a typical reaction which is given, okay, where these two join together and generate 001 type. Okay, if we calculate energy, this will be 3/2 plus 3/2, correct? No, 3/4. 3/4 plus 3/4, right? that is two types of dislocation. This is essentially going to be 1. Here it is 3 by 4 plus here it also will be 3 by 4. This is b squared value we calculate. So this will turn out to be that is 3 by 2, correct? Yeah. So whereas that is high, so this reaction is also favorable, but as such the Burgess vector of this dislocation is quite high. Correct? What has been observed is that when this dislocation has got a tensile configuration, okay, during that time, generally if you look at when this dislocation has got a edge configuration, okay, for an edge dislocation, we look at it like this. This is how, this is where the tensile stress is going to be there. The compressive stress is going to be there in these directions, okay. When the Burgess vector is large, it has been observed that under tensile loading, these regions act as nucleation for crack to develop, okay. That is below the extra half plane where the tensile stress are going to be there. In many of the crystals, it has been that these H200, the edge dislocations with Burgess vector 100 type which form, they don't have no role in the plasticity, but they do act as crack nucleation sites. Okay. So far we have considered perfect dislocations, okay, 111 type, the screw and the edge. Similarly, 001 type dislocation also, what is its effect we have considered. That's and in most of the BCC system, the experimental observation is that they do show twinning during deformation. Okay. What is the mode in which the twinning can happen? Okay. The stacking sequence along 112 direction is essentially a 6-layer stacking. To understand the stacking sequence, what I had shown is a close packed 110 plane, okay. In this plane, this is the 001 direction, this is the 112 bar direction with respect to the specific plane, this is the Burgess vector, okay, is showing the, no, this is actually wrong, this is essentially 1 by 2, 1 bar, 1, 2, that's essentially the B, what is being shown is half 111, okay. So the stacking sequence is, this is I think 2 layers of BCC, one on top of the other has been placed, and then what we are trying to look at it, the projection of the atoms on 110 plane. If this is the A plane, the B plane 112 type of a plane, this will be the one. This is the C, D, E, F, because that if you look at that, then A plane comes, this is on that vector that A atom position matches, okay. This is how the different layers are stacked one on top of the other. What we are showing it is a projection. In fact, if we look here, this C position, one A atom is also going to be there in this plane, the C atom also overlaps with it. Similarly, this shows the projections which are on the layer which is above. All these circles which are being shown are atoms which are overlapping one on top of the other. Here what is being shown on the one which is above or below, we can consider it, okay. What is essentially important is that if by a vector, 1/3 of this vector if I take it, so essentially it will be from here to here if I move, this atom will move from here to here, Similarly, this atom will move from here to here. That this atom moves from here to here, this will be close to A position with respect in this direction, it is close to F, right? So, the position of the layers will be shifting, okay. This shift of position is shown here in this stacking sequence. Here what I have done, I am just showing here one particular layer, okay. The perfect stacking sequence is there, A, B, C, D, E, F along 1, 1, 2 direction. This shows that this layer is being now shifted by a vector A by 6, 1, 1, 1. So, when this is shifting, this B comes to C, C comes to A, like that they shift. Then the next layer after that has happened, that is on every successive layer, okay, a displacement of A by 6, 1, 1, 1 is being incorporated. By giving a displacement of that vector, now this A position will be shifted to E position. Like this, if we consider everywhere, here that this position gets. So, finally what happens, we have a stacking sequence which is there after 6 layers, A, B, C, D, E, F, A, F, E, D, C, B, because this is a mirror image of the other. Okay. So, essentially we have formed a twin. So, R, this same thing is being shown here, where this side is an untwinned lattice. When a displacement vector of magnitude A by 6, 1, 1, 1 moves on every plane, then they shift the atoms to the positions. You see that now here it has come to this position, here it is identical to. So, mirror image is being created. This way twins can be created. Okay. This is the mechanism which has been put forward for twin mechanism in BCC. If you remember, in FCC the twins are essentially on 1, 1, 1 plane, 1, 1, 2 direction. Here on 1, 1, 2 plane, 1, 1, 1 direction is where the twinning is taking place. Okay. There it is a 3-layer stacking sequence, and here it is a 6-layer stacking sequence. So far what we have considered, the different types of perfect translation vectors in BCC, okay. Their movement in close packed planes, okay, whether fault will form or not. Then what is the mechanism by which a twinning could occur in BCC lattice, okay. Like in the case of a prismatic loop which we have seen, whether the prismatic loop can form in BCC lattice also or not, okay. That is what we will consider, because in FCC, okay, by condensation of vacancies, okay, or accumulation of interstitials in close packed plane, okay, frank dislocations or prismatic dislocations could be formed. Here also along this 1, 1, 0 plane, suppose we remove one particular plane, small region of it, okay, it will generate a loop, okay. But normally what has been seen is that this sort of loop if we create, okay, that is because the stacking sequence is AB, AB, AB type of a stacking sequence. If I remove one plane, okay, this plane is removed. Now the stacking sequence A position comes on top of an A position. But what is interesting here is that if by a movement of another perfect translation vector, if it reacts with it, it will move the B position to an A position to a B position. So essentially a movement of perfect translation vector can restore the order. Okay. So these faults need not occur in the normal circumstances, but during irradiation, okay, faults, these sort of, not faults, during irradiation, formation of dislocation loops, okay, has been seen in BCC lattices. Many of the BCC, especially irradiation, during irradiation. Okay. Computer simulation of these loop sizes, how they look like, all these things have been looked at. Okay. And it has been seen that many small clusters are there with half 1 Burgess vector. Okay. Also, especially in iron, it has been seen that some loops have been seen with 100 type of a Burgess vector also. Okay. Here, what are the different types of possible reactions by which these loops could form is given. Okay. So, with this we had looked at briefly what are the types of dislocations which can form in BCC lattice. We have not gone into looking at any specific system. Okay. The interaction between dislocations, its discussion of those aspects is beyond the scope of this work. But if one looks into a literature, lot of data is available where people have published papers, okay, where they have looked at interaction between various types of dislocations in BCC lattice. But what we had shown here is that what are the types of dislocations which can form, and which is the type of a dislocation which is mostly seen, like during this discussion last half an hour, okay, one could make out that it's essentially 10, that is screw dislocation. Perfect screw dislocation is the one which is mostly seen in BCC lattice. Okay. Let us look at, because HCP crystals are also important one, because zirconium, titanium, these alloys, they crystallize into HCP form. Okay. The temperature at which you wanted to use them, they are always in hexagonal close packed state. Okay. Let us look at the crystal structure of hexagonal close packed lattice. Okay. In a hexagonal close packed lattice, okay, only one close packed plane is there. Right? That is called as the basal plane, which is shown by light blue color here or violet color. Okay. The atoms in the basal plane, if we consider the hard sphere model, they touch each other. Okay. And in between one more layer comes, which is displaced by a vector, okay, A by 3 1 0 1 bar 0 type, okay, and then another layer comes. The stacking sequence in this case in HCP in close packed plane is essentially, or the basal plane stacking is AB type of a stacking sequence, correct? This is the way the stacking sequence goes. Okay. What are the Burgess vectors which the dislocations can have? Perfect dislocations. Okay. One is that this is one close packed direction, this is another close packed direction, this is the third close packed direction. All of them are lying on 001 plane, correct? This is the basal plane. Close packed direction is 1 by 3 110 type. Okay. In fact, this dislocation, with perfect dislocation with this translation vector, lies not only in this plane, it is lying on 0 1 1 bar 0 type of this plane, which is perpendicular to the basal plane. Okay. And this can lie on a plane like this from here to here. This is called as the pyramidal plane. Okay, that is 1 bar 0 0 type of planes are called prism plane, are called as pyramidal plane. Okay. So these are all the planes in which this dislocation can lie. Okay. So far we considered only one translation vector. Okay. This translation vector turns out to be the smallest perfect translation vector in HCP lattice. Other translation vector is along the basal plane. These planes are 0 0 1 planes are close packed. Okay, they are stacked one on top of the other along a AB type of a stacking sequence. So a vector going from here to here is also a perfect translation vector. And the nomenclature in especially people who work on zirconium or titanium alloys, okay, they use the terminology that 1/3 2 bar 110 type of a direction. They call it as an A type of a dislocation because that is along the A lattice parameter, correct? A direction. And this is along the 0 0 1 direction, that is where we consider the C axis. So they call this as the C. And another is, if I take a vector from here to here and from here to here, this vector addition will give one from here to here, this vector. Okay, that's also a perfect translation vector. That vector is called as the C by A dislocation. Okay, it's essentially nothing but A plus C adding together, that vector gives another perfect translation vector. Okay. Out of which vectors, if we consider the dislocation with this perfect translation vector, that is the perfect dislocation with this Burgess vector 1/3 2 bar 110, okay, it can move on 3 slip planes, correct? All others just essentially move on only one particular type of a slip plane. That's one. Another is, what are the types of partial vectors which we can have? Because here also it's a close packed plane. Okay. To understand this better, okay, similar to what has been done in the case of an FCC material, we can make a Thomson tetrahedra, okay, and try to represent all the slip planes and the slip directions, okay, or essentially the slip directions which is being done here. Here, if you look carefully, I had marked this as A, B, and this is C, and this is S. And all these atoms, this is a tetrahedron, like a Thomson tetrahedron. Okay. Only thing is that the plane containing ACB is the basal plane, correct? And if I consider the midpoint of it, okay, this, yeah, A sigma, C sigma, B sigma, all of them will generate partials, correct? Then if I take a distance from here to half the distance, because 0 0 1 corresponds to a perfect translation vector, half of it will create essentially a partial vector, correct? Then these are all the slip planes. But here the problem essentially is that in this way we have represented it, the one perfect translation vector which is from going from here to here, we are not able to represent it. For that, what is being done is a double tetrahedron. That is, one tetrahedron is there, you join with another tetrahedron which is going to be there at the bottom, you just show that. Once that has been taken, not only these vectors on the basal plane, that is AB, BC and AC are the perfect translation vectors in basal plane. Okay. This ST represents the perfect translation vector, okay, perpendicular to a basal plane. Then this vector SA plus this vector TB, if we take it, that will represent the vector from A to this point. Okay. These are all considered as the three of the shortest translation vectors in HCP lattice. If you look at the Thomson tetrahedron, that AB, BC and AC are the perfect translation vectors, okay, and that is generally designated as A, okay, and this is the magnitude, this is the Bayes vector, and from this we can find out the magnitude. ST is another perfect translation vector, it's called as the C, and the vector is 0, 0, 0, 1. Okay. This is the convention which is used to represent this vector SA plus TB, because these two are at two different points. Okay. So SA stroke TB it is written, that's nothing but a vector sum of SA and TB. Okay. That generates C plus A dislocation. Okay. And these vectors A sigma, B sigma, C sigma, they generate partial translation vectors. Okay. Now, in this table, okay, shows with respect to C by A ratio, okay, which are the plane in which slip can occur commonly in different hexagonal materials which have got hexagonal crystal structure. If it consider a hard sphere model like this, putting atoms on top of it and try to construct it, that hexagonal close packing if we take, okay, then the C by A ratio in an ideal case is 1.633. If you look at titanium and zirconium, the C by A ratio is less than 1.633. Magnesium, cobalt, zinc, cadmium, okay, if you look at that, magnesium and cobalt has got values close to 6.633, beryllium is a very less value, zinc and cadmium has got a value which is high. Okay. Generally what has been seen, the one which has got a C by A ratio less than 1.633, there the slip has been found to occur on 1, 0, 1 bar 0 type of a plane, though the closest packed plane is the basal plane which is 0, 0, 1. Whereas in cases where the C by A ratio is close to 1.63 or higher, on basal plane is where the slip has been found to occur. Okay. And beryllium is an exception where even with a low value of C by A ratio, which is smaller than an ideal case, okay, still in basal plane deformation occurs. Okay. In this transparency, what I had shown is the different vectors, Bayes vectors of perfect dislocations. Okay. What is going to be the magnitude of these vectors, okay, and the B squared value to find out the energy, that is self energy of the dislocation. Okay. One interesting thing which we can consider it is that if two perfect dislocations, like we have seen that in the same slip line, okay, a dislocation AB plus BC can give rise to CA, the same type of a reaction which it can happen, AB, BC, CA, RAC, all of them are perfect translation vectors in close packed plane. Okay. If a dislocation with a Bayes vector AB interacts with another BC, this should give rise to won't be the vector AC. The AC is also a perfect dislocation with a perfect translation vector. Okay. So, essentially what is going to happen is that this sort of a reaction has often been seen in many HCP materials, and these dislocations join together to form a network. Okay. Some hexagonal network of dislocations have been, which one can see in many HCP material. Okay. Suppose we assume that these dislocations, because we have seen that each of these dislocations with these translation vectors, perfect translation vectors, that is 1 by 3, 1, 2 bar 110 type of a Burgess vector, okay, they can lie on prism plane. Okay. Each one of them can lie on different type of a prism plane, because that's what it will happen. If that is what the case and the dislocations are moving in those planes, okay, they can come and interact. What is the sort of interaction which can occur? There what happens is that if and another thing also which we should notice is that for each of these directions, if we consider, that is the dislocation with this Burgess vector, the prism plane is specific only in that plane. So, in another plane, okay, another specific dislocation is there, a type of a dislocation. These dislocations, when they interact, okay, they will be generating another dislocation of the type AC. But this AC dislocation turns out to be like we did it in the case of an FCC material, dislocations lying on different slip planes when they come together. And this interaction, if you look at this reaction, this is an attractive reaction, so it's possible, and they generate another dislocation which is an A type, but it lies on another prism plane. If it lies on another prism plane, it can easily move, whereas in the case of FCC material, it is lying on a not on a close packed plane. Because of that, the dislocation becomes sessile. Right? Here that does not occur. These reactions generally generate a dislocation which is essentially a glissile dislocation. Okay. Then now let us look at what are the type of stacking faults which it can form. Okay. The other type of dislocations also other than dislocation with this A type of dislocation, okay, C plus A dislocation has got a large Burgess vector. It has rarely been seen, okay, under heavy deformation and all, but otherwise most of the time these type of dislocations which are observed. Okay. What are the types of faults which it can form? Because this is also a close packed plane, and in this close packed plane, every atom, that is the next layer, when we place an atom on the next layer, it can be placed on two positions. On A plane, B and C positions are there where an atom can be put. But essentially the stacking sequence is AB type of a stacking sequence, correct? In this type of a stacking sequence, okay, suppose I remove one layer, okay. If I remove an A layer, then what it will become? The stacking becomes AB, AB, AA, no, AB, AB, B, AB. This is the type of a stacking sequence which will happens, correct? In this particular type of a stacking sequence, if it interacts with another, this will be a high energy fault. If it interacts with another partial which moves this to C position, AB, this will become C, this will become B, C. That is AB stacking sequence that changes to a different stacking sequence. On the other side also it's an AB-AB stacking sequence, but with a fault which is coming in between. Because of that, the same stacking sequence is not being followed. Okay. This is by removal of a plane and a slip by 1 by 3 1 0 1 bar 0 type of a vector, which is a partial translation vector. Okay. What is the other way in which it can happen? Okay. If a vector by 1 by 3 1 0 1 bar 0 type of a partial which moves on a some particular plane, okay, what it will do when the stacking sequence is AB, AB we consider it. Suppose we assume that here it moves this B layer, okay, will be moved to a C layer position, correct? B layer moves to C position, then what will happen to the A layer will go to a B position, B layer will go to the C, this will go to the A, this will go to B, this will go to C. That means that the stacking sequence from ABEB it changes to CBCB. But a movement of a partial in the case of an FCC lattice, okay, a fault is created, but if you look at the stacking sequence on either side of it remains ABC, ABC. But only thing which we should notice here is that a 3-layer stacking has been introduced here, which is similar to that of a BCC, which is similar to that of an FCC. So essentially, a unit cell of FCC is created in hexagonal post-packed cell, okay, by generation of a stacking fault. Okay. These are all essentially intrinsic stacking fault. Okay. The extrinsic stacking fault can be generated, okay, if we add a layer, okay, that is in this stacking sequence assume that we add a layer either here or we assume that we add a layer here. Between B and A, we are adding a layer in the C position. So this becomes okay. Here, either side of it, if you look at it, it looks like AB, AB, and the other side also AB, AB, okay. But an ABC stacking has come in the middle, okay. This is an extrinsic stacking fault. These are all the three possibilities. People have done a lot of calculations to find out in many of these crystal systems, okay, what is the energy of these faults. Okay. It has been seen that the stacking fault energy of the extrinsic stacking fault is the highest. That of this fault which is shown in the middle, this one, it is going to be intermediate, and this has got the lowest fault energy. That is the observation. But generally, these fault energies are very high. Okay. Normally, faults has not been observed in either in zirconium or titanium alloys. Okay. But this sort of fault in principle can form. Correct? Yeah, most of this one. Here also under alloying additions in some of the materials had been seen, but normally otherwise in pure zirconium or this one if you consider it, generally these sort of faults are not seen. Okay. This is essentially showing the structure of the faults with the ABC stacking sequence when a perfect dislocations, that is if a perfect dislocation splits into a partial, okay, then that partials if they separate, they should be able to generate a stacking fault. And normally this has not been observed in many of this material. Okay. Generally, on prism planes, that is, suppose the deformation like zirconium and titanium, essentially the prism plane is where the slip is occurring. Okay. With A type of a dislocation. That is, A type of a dislocation has got a Burgess vector of this type. Okay. Then these dislocations, they can split into two types of reactions, which has been thought of that they can split into partial, okay, and they can generate stacking faults. Okay. But the observation is that this sort of deformation has not been observed at all. Okay. That is the truth in both these systems, zirconium and titanium. In fact, in all these systems, essentially, if one looks at it, okay, the number of independent slip systems which are available for slip in HCP material are 2 in prism plane and 2 in this one, totally only 4. The number of slip systems, von Mises criterion says that we should have 5 independent slip systems are required, okay, to compensate for that. Some of the dislocations with Burgess vectors which have got higher magnitude, either they are generated or in many systems twins do form. Okay. Twinning has been observed in many hexagonal close packed materials. Okay. The twin, I will not talk about it here. Okay. Maybe when we talk about twinning as a separate topic, then we will consider this. Okay. So far what we have done, we have looked at the different type of dislocations which it can form, perfect as well as the partial. Though we have considered the various reactions by which partials could form, in general it's the perfect dislocations which are responsible for slip in HCP system, correct? And in HCP systems also, since these are closed packed planes which we are stacking, okay, removal of a condensation of a vacancy in one plane, okay, or accumulation of interstitials in a plane, closed packed plane, like frank dislocations, we can form some dislocations here as well, like vacancy loop or interstitial loop, that sort of a reaction. But here the things are seen to be much more different from that of what has been seen in hexagonal closed packed system, because here what happens, if a condensation of a vacancy takes place, like in this case, then you find that 2 BB atoms are coming close together. Okay. This essentially generates a high energy fault. In the case of FCC, when a condensation takes place, they can generate a low energy striking fault. That just does not occur here. Okay. Now, in this particular case, okay, by a movement of another partial, okay, of the type sigma b, okay, this could be converted into, this B layer could be moved to a C layer, okay, so that an intrinsic striking fault could be generated. That is what it's expected to happen. Okay. Actually, the same thing which I had explained, okay, I had shown here, because when this one dislocation moves and changes it, then you can see that the nature of the vector, okay, the extra plane which is going to be is not in the slip plane. Okay. These are all the types of reactions which it can occur. So essentially what we have considered is that from the crystal structure, what are the types of translation vectors which can occur in BCC and HCP lattice, okay. And in principle, they can split and generate, split into partials and generate striking fault, but the experimental observations as well as some of the theoretical calculations and computer simulations show that that just doesn't occur. Okay. Now I'll stop here. Okay. If one wants more detail about the various types of dislocation and dislocation interaction, one can go through other books in detail. Okay. But that is beyond the scope of these lectures. Okay. In the next class, we will look at essentially multiplication of dislocations and interaction of dislocations. We will look at it in some detail. Okay. We will stop here now.